All right, good afternoon, everyone. How was your weekend, guys? Good. Good. Are you happy with the Super Bowl result? Or don't even care about that? I didn't know it was a Super Bowl until a friend told me yesterday. I don't pay attention too much to it. Okay, guys. I just wanted to go quickly to the syllabus. You're starting to work on your homework, so remember that Mohammed and Jeffrey are going to be available at this time to help you out. If you don't see them at that time, just email them, but they should be there, okay? Or just let me know if you can also tell me that hey, they haven't been showing up. I'll talk to them. Yes, TA. So we have TAs helping. All right. So we have been already through this material. First week and second week, we know about pore pressure, stresses, and horizontal stresses. What's the problem?
Writing red. Turn off.
No, I think it's recording.
Okay.
It's a recording.
Yeah. Okay. So something very important that you got to know now is that we have horizontal stresses, but still we don't know how to determine those, and that's what we want to work on today, into finding a method to understand a little bit better what is horizontal stress, how you can calculate that, or how you can measure that. And before we go in there, we'll talk in a little more of detail about stress, how we can express stress in 3 dimensions. Because so far, you know about stress, but it's mostly in 1 dimension. So this direction where we are going. And also we're going to make a difference with some other quantities that you already know, and you will see how different those are. In order to do that, we'll make an example of a place where you drill. Let's say in this example that you go with the lateral wellbore.
Professor?
And yes.
Could you turn off the autofocus?
Let's see if it works, because that time it didn't work that well. But I'll try. Okay, so let's say that at this particular location, we want to make a hydraulic fracture, and we know by now that ideally that horizontal well should be drilled in the direction perpendicular to the minimum principal stress. Okay? That's all I'm going to tell you right now. And let's start thinking about some properties about this reservoir. What can you tell me about this reservoir? Let's say, what do you decrease in order to produce? Pressure, right? And at this particular location, let's say that pressure is equal to 8,000 psi. And I'm going to say so because I'm going to assume that the depth up to this point is about 10,000 feet. If the depth is 10,000 feet, what is going to be more or less the vertical stress? 10,000 psi, right? You should remember, onshore, more or less, the overburden is 1 psi per foot. So the stress is going to be 10,000 psi. I'm not going to write it back right now. I'm just going to say for this example that SV, I'm imposing this. It may not be necessarily true all the time. I'm just saying that this is correct. And what do you think? Well, I already told you what pore pressure would be Does that look like hydrostatic pore pressure? What do you think?
No.
No, right? Because it's higher than what you would expect for hydrostatic pore pressure. What would be the pore pressure that you would expect for hydrostatic?
4,300.
Times 10,000, right? How much is that?
4,000.
Around 4,000, 5,000, right? Something like that would be hydrostatic. Notice that pressure in this case is just one number. One number tells you everything to characterize pressure. Can you tell me any other quantity in this reservoir that we can characterize just with one number? Temperature, right? Let's say temperature in this case is 200 F, okay? Is one number. And another example could be, for example, oil saturation, let's say 0.7. All those quantities are represented just by just one number, and in mathematics that goes by something which is called a scalar. And what that means is that if we have, for example, a coordinate system over here, X, Y. Let me draw this axis in the other direction. So it's X. This X, this one is Y, and this one is Z. Then it doesn't matter if you were to use this coordinate system or another coordinate system, this value will be always the same. It doesn't change with the definition of the coordinate system. But that doesn't happen with all properties. Let's say that, for example, now here at this location, you open a hydraulic fracture, which is on the plane of the bore, and the piece of rock that at the beginning was somewhere over here moved a certain amount because now the hydraulic fracture is open. And that has what we're going to call a displacement U. What is U? It's a vector, right? It's a vector because it's going to have three components. For example, let's say in this case a U, look, the first component is going to be in the direction of X, and let's say is equal to 2 millimeters. What is the component in Y?
0.
We're going to say in this case is 0. And component in Z looks like 0 too, right? So that's a displacement. That's a vector. Can you give me another example of a vector? Let's say that we are producing, and probably we'll make another fracture over here, and the pressure around here was, we said, 8,000 psi. Originally, in order to produce, we said we have to reduce the pressure. So let's say that somewhere over here we have 6,000 psi and quite a big pressure drawdown. Let's make it a little bit smaller, let's say 7, okay? And the volume for pressure is 6,000 psi. As a result of the difference of pressure, what are you going to have? Which vector? Oh, a Q, right? Q, which is a fluid velocity. So Q is going to be in that direction, and it's also going to be a vector. Q in this case looks like it's also aligned with X. So let's say that Q is 1 feet per day, and this is 0, and this is 0, 2. These two examples of vectors, they wouldn't be the same if I were to use another coordinate system. For example, if I were to use a coordinate system that is like this, that this is x prime, y prime, and z prime. That's a valid coordinate system. I could use that. Nothing tells me to use this one opposed to that one. But notice that now if we have to write the vector in this coordinate system, it's not going to be the same. The components that are non-zero here, they're going to go in this third position. So the message is that the vectors now depend on the coordinate system that you choose. And now there's going to be another type of mathematical element that we're going to use a lot, which is called a tensor. The tensor like stress, if this one was one number, this one is a vector, what do you think the tensor is going to look like?
3D.
It's going to be a matrix. It's going to be a matrix which in general is going to have, because we're working in 3 dimensions, it's going to have 9 elements, and I'm going to call these elements with the first index is the row, and the second one is the column, and they're going to be 9, as I said before. So, what do they mean, those 9 numbers? Those 9 numbers are going to have in the diagonal the normal stresses. So if I were to take a piece of rock somewhere over here, a little cube, which is going to be this one. In the diagonal, as I said, you're going to have the normal stresses, and in this case, this one is going to be what I'm going to call S11. This is going to be S22, and this one is going to be S33. I could also use SXX, XYY, and XZZ according to that coordinate system, but since I already wrote this one, S12, I just wanted to keep it like that. But remember that here the 1 corresponds with X, the 2 corresponds with Y, and the 3 corresponds with Z. Those are going to be the normal stresses applied on this element of solid. So, can you tell me now, according to what I just said, that diagonal terms are going to go here, which one is S11 in this example? It is SH mean, right? Which one is going to be S22? SH max, very well. We didn't talk so far about SH max, but that's going to be perpendicular to SH mean. And the third one, S33, is going to be SV. Okay, so we have normal stresses now. Now we are going to write the shear stresses. Diagonal terms, remember, are always normal stresses. The off diagonal terms are going to be the shear stresses. But let's just keep the shear stress for now. I'm gonna assume the shear stresses are 0. So I'm going to fill all of these with zeros. And that's what I have for my example. And let's put some numerical values on this example just to complete it. If the pore pressure is 8,000 and the overburden pressure is 10,000 psi, what do you think is going to be the effective vertical stress? 2,000 psi, right? We're going to see later on that usually the minimum horizontal effective stress for this type of normal faulting regime, you can calculate the effective horizontal stress as more or less 1/3 of the effective vertical stress. We'll see why that later on. But if I take the rule, I could say that SH mean is more or less 600 plus 8,000, which is 8,600. And just let me assume that. So here we're going to have 8,800. Here we're going to have 10,000. And SH max, let's just say that
Could
it
you use
is
the paper?
9,000. Yes. PSI. So now you have all the numerical values for this state of stress. The same as the vector, the tensor is also going to depend on the coordinate system that you choose to write that stress. So if you want to fully describe a stress tensor and state of stress in general, remember that you're always going to need 3 quantities. And not only that, but you're going to need also 3 directions. You need to know in which direction those are oriented. In this example, I said it is oriented in this one, direction of x, but it could go in any other direction. And if you remember the example from the Barnett shale, the horizontal stress were oriented at an angle from the north, about 60 degrees